All right. So welcome everyone. So the first talk for today is by Armen Shirikyan, who'll speak about mixing for PDEs with degenerate noise, an overview on open problems. Please, Armen, floor is all yours.
Thank you very much. Thank you very much for the invitation. It's a big pleasure for me to give this talk at this conference. So I will be talking about the problem of mixing of PDEs with degenerate noise. And I'll begin with a short description of the contents of this talk. So I'll begin with an introduction to tell you what this talk will be about and to outline the problem I'm going to discuss. Then I present two results about uniqueness and stability of stationary measure for Markov processes generated by PDEs with random forcing. So I present two results describing different types of degeneracy. Then I'll show very briefly how those results can be applied to the problem of mixing for the Navier-Stokes system. And I conclude with three open problems. So let us consider the two-dimensional Navier-Stokes equation with degenerate random forcing. So this is our Navier-Stokes system. It has three equations. This equation is, in fact, a pair of equations because u is a vector valued function. It is the velocity field of the fluid. And you have a third unknown function. This is p, which is the velocity, which is the pressure of the fluid. Everything is considered on the two-dimensional torus, even though some of the results will be true on a general domain. So we have three equations for three unknown functions. So this is the equation of motion, and the third equation is divergence-free condition for the vector fluid, which means that the fluid is incompressible. So if incompressible viscous fluid in a two-dimensional torus. Here you have a parameter nu, which is a positive number. It will be fixed, but it can take any value. And you have two differential operators, u nabla, which is defined this way. It is the transport term, and delta, which is the diffusion term. Well, the system is subject to external force, which I have written in the form h plus E2 of tx. So here h is a deterministic function. It will be sufficiently regular. And you have also a random forcing E2 of tx. This is the most important object of this talk. There will be some conditions on this forcing. The equation is supplemented with the initial condition for the velocity field. U at 0 is equal to u naught. And a well-known result says that equation 1, 2 is well posed in the two-dimensional case, and it generates a flow in the space H, which is the space of square integrable vector fields on the torus, which are divergence-free. In principle, this is enough to define the flow, but I also impose the condition that the mean value of v with respect to x is equal to 0 to ensure that the energy, or at least the mean value of the energy, remains bounded as a function of time. Now, concerning the random forcing, I will consider two types of degeneracy. The first type, which I call F, is for Fourier, is a forcing which is localized in Fourier space. In other words, I fix an orthonormal basis. For instance, I can take the standard trigonometric basis in the space H. Then it would be natural to index them by a integer lattice without origin, because I have to remove the origin because I assume that the mean value with respect to x is equal to 0. So I fix a subset. It can be also infinite, but the most interesting case for this talk is when lambda is a finite subset. So I take here a finite sum, and each Fourier mode in this sum is multiplied by a stochastic process, scalar stochastic process, which I denote by eta j. Concerning hypothesis on the stochastic process, I will talk about the hypothesis on the next slide. And the second type of degeneracy is when the noise is localized in the physical space. For that, I fix a basis, orthonormal basis in the space H10. I fix a domain D on the two-dimensional torus, and I fix a basis here, orthonormal basis, and I take the sum from 1 to infinity of eta j. Again, there will be some hypothesis on this eta j multiplied by phi j. Well, in principle, you can take here also a finite sum when your new parameter nu is fixed. But even if you have infinite sum, the noise is still degenerate because it will be always supported in this domain D. Well, both these noises are degenerate in the following sense. The Navier-Stokes equation satisfies what is called Fourier-Prodi property. And it is the following property. It says that for some finite dimensional subspaces, for instance, if you take sufficiently many Fourier modes, you have the following implication. If you have two solutions such that the projection of the difference to this finite dimensional subspace goes to 0 as time goes to infinity, then the difference of these two solutions goes to 0 as time goes to infinity. So in that sense, this subspace determines the behavior of solutions as time goes to infinity. So neither of these two subspaces, finitely many Fourier modes, the subspace generated by finitely many Fourier modes, or the subspace of functions supported by a given domain, are not determining subspace. At least they are not known to be determining subspaces of Navier-Stokes system. And in that sense, the two noises are degenerate because they do not act on a determining subspace for the Navier-Stokes dynamics. Here are the hypotheses concerning the dependence of these eta j, the coefficients in the development of the noise, on time. So we assume that they are such that the corresponding dynamics is Markovian. In other words, if you consider all possible solutions corresponding to all initial data, then you will have a family of trajectories, and that family of trajectories is a Markovian process. Well, one widely used process is white noise in time, which means that we take independent Brownian motions, take the time derivative, and multiply them by some coefficients bj, which are supposed to be positive. And the second one, what I call piecewise independent noise, is the following. So I divide my time axis onto intervals of length 1, right? K minus 1k, and k runs from 1 to infinity. So each interval, it has a length 1, and it is the interval between the two consecutive integers. So on each interval, even though I have an infinite sum here, in fact, each sum contains only, each term is supported on this interval. So for any t, you have only one term which is not 0. All other terms are 0. Then I take an orthonormal basis psi I in the space L2, and I translate it to the interval k minus 1k. Right. So this psi A, when I subtract k minus 1, it is a function of t varying in k minus 1k, and then I develop my function in this basis. So we have coefficients bij, just some numbers, and randomness comes from here. Psi I kj is a scalar random variable, and I assume that they have the corresponding low has a density with respect to a Lebesgue measure. This density is C1 function, and the support is in -1, 1. So this forcing will be bounded with probability 1, in contrast to the white noise, which is unbounded. Well, of course, when you consider an equation with this forcing, you will not have Markov process when t belongs to R, but when you restrict yourself to integer lattice, to integers, then you will have a Markov process. And in both cases, the problem is the following. We need to find sufficient conditions on the random forcing which ensures the uniqueness of stationary measure and stability or mixing as time goes to infinity. So this is the problem I want to discuss here. Now, before doing that, I would like to mention some references on the subject. When the noise is localized in the Fourier space, the first result was obtained by Heirer and Mattingly. There was a series of 3 papers between 2006 and 2011, and they considered the Navier-Stokes system either on the torus or two-dimensional sphere, and also some other equations like reaction diffusion system. And in the case when you have white noise on the right-hand side, multiplied by finite many Fourier modes, they have proven the existence, the uniqueness of stationary measure and the exponential mixing in dual Lipschitz metric. Then there was a work by Foldes, Glatholz, Richards, and Thoman, who considered Boussinesq equation. So this is again a system of equations, and you have equation of motion plus the equation for temperature. And assuming that the noise acts only on the equation of temperature, they prove the uniqueness and exponential mixing. In joint work with Kuxin and Nersessian, we studied again the noise which is degenerate in the Fourier space, and we studied the second type of noise when you have bounded noise. This allows to consider some other problems which cannot be handled in the case of unbounded noise. Concerning the second type of degeneracy, when the noise is localized in the physical space, as far as I know, there are not many works. I studied the case when the noise is either distributed in the domain or acts through the boundary. And there are some, I would like to mention some other works for some other PDEs, which again consider the case of degenerate noise, but these PDEs possess some specific properties like contraction in the L1 norm or order preserving properties, and are not likely to apply to Navier-Stokes system. Nevertheless, I would like to mention the work of Sinai in 91, who proved that the Burgers equation has a unique invariant using stationary measure. The work of Bartin, Kator, and Hanin, again Burgers equation, but in a much more complicated situation on R with no decay condition to infinity. And the same problem was studied recently by Dunlap, Drum, and Rijik for different type of noise, and also the work of Budkovsky and Shuitsov for order preserving PDEs. Well, as I mentioned before, so I will not discuss this type of degeneracies in this talk. Well, now I move to the first section about the results. So I will begin with some abstract random dynamical system. So let's fix two Hilbert spaces, H and E, and let's consider map S, which acts on the product space with range in H. So if I fix also an independent sequence of independent identically distributed random variables in E, then I consider this random dynamical system. I start from point U, and then to determine U at time k, I need to take U at time k minus 1, my random variable number k, and apply S to this pair, uk minus 1 e to k. Well, the relation of this random dynamical system with the Navier-Stokes system is very simple. It can always, Navier-Stokes system can always write in this form. Why? Because it suffices to take, to denote uk, the solution at time k, to take, for instance, E to be the space of square integrable functions with range in our finite dimensional space, or with range in a space of functions with support in a given domain. Then for both type of noises, be it white noise or piecewise independent noise, you can choose random variables e to k which will be independent, and you can write your solution as a trajectory of your random dynamical system 5. So the result I'm going to present will concern this random dynamical system. Due to independence of this e to k, the family of all trajectories form a Markov process. And the hypothesis I will impose on this system will ensure that there is at least one stationary measure. So here are the hypotheses. Let us denote by L the law of random variable CTK. So this will be a probability measure on the space E, on the Hilbert space E. And for this talk, I will assume that the support of L is bound, is a compact subset. So this means that I do not consider the case of white noise. The case of white noise involves additional difficulties related to the unboundedness of the phase space. This hypothesis that K is compact will ensure that essentially my phase space will be bounded or even compact. And then I impose the following hypothesis. The first one is that this map S, which acts on the product space, H times E, is C2 smooth in the Fresher sense. In the context of partial differential equation, this is basically nothing. Because if your problem is well posed, then very often, at least in the parabolic case, you have even an authenticity of dependence on data. In hyperbolic case, you may lose some regularity, but still you have regularity of the resolving operator. So this is just an assumption which is essentially always satisfied in the context of partial differential equations. To formulate the second condition, let's impose the domain of attainability from a given set. So let us fix a subset B in the phase space H, and let us define the following sequence of subspaces, subsets. Well, A naught is just B, and to find AK, I need to take all what I can get at step K minus 1, and I consider all possible controls, all possible values of the random variable. So I take anything in this support, and I apply S to these two arguments. So this is indeed the domain of attainability from a given set B using control or using right-hand side which belong to this support of the measure. And then I assume that there is a compact set X which is absorbing. In this sense, I will make comments, and is invariant. So invariance means that if I take any point in the set X and any element of K, then S applied to this will be in the set X. And absorption means that for any bounded set B, I can find an integer such that no matter what you choose in as a control or as a right-hand side, you will end up in the space in the set X. And due to this invariance, in fact, you will stay there forever. Again, in the context of dissipative PDEs, this condition is more or less always satisfied. There is an entire theory of attractors which gives you sufficient condition for this type of results. And again, in the context of Navier-Stokes, this is very easy to check. Now there is a third condition which I will formulate, but I will not discuss sufficient condition for that. This is a non-trivial condition. It says that you must have approximate controllability to a given point in the following sense. There is a point in this absorbing invariant set X such that if you take any epsilon, any initial condition, and some suitable integer K, which depends only on epsilon, but not on the initial condition, then you will have this, which means that, well, I didn't introduce this notation. So this means that, sorry, I should have written here, instead of S, I should have written here A. I'm sorry, there is a misprint here. This is not S, this is A. Domain of attainability at time K minus K epsilon, starting from U naught and with control in eta. So you can choose controls such that at time K epsilon, you are in the ball of radius epsilon center that you had. So this is property of approximate controllability of to the point you had. Well, this is non-trivial property. There is one case when it is always satisfied, when you take right-hand side which does not have deterministic part, when h is equal to 0. Then 0 is globally stable equilibrium point for the Navier-Stokes dynamics, and it suffices to take 0 as a control. All solution will converge to 0, and therefore you have approximate controllability to 0. But there are some other cases when h is non-zero, you still have this property, but I don't want to discuss this property at all because this is not the main point of this talk. And finally, the composability of the noise. There is an orthonormal basis in the space E and functions rho s, which are continuously differentiable, such that the law of the noise, the law of eta k, can be represented as a tensor product of its one-dimensional projections. So here PS is the projection to the vector span of GS. It is just a straight line. So I take the projections of L to the straight lines, and my measure L, which is the law of my IID sequence eta k, is representable as a tensor product of these one-dimensional laws, which possess densities with respect to Lebesgue measure. Well, for the noise I presented, this condition is certainly satisfied. And here is the first result. To formulate it, let me remind you that you can introduce the following metric. It's called dual Lipschitz or Kantarovich-Wasserstein metric on the space of probability measures on X. Well, it can be also on H, not necessarily on X. So it is defined this way. So I'm measuring the distance between the measures on this bounded part of the space. I take all Lipschitz functions on X, and I take the integral of the function f with respect to mu1 and the integral of f with respect to mu2. I consider the difference, the absolute value of difference, and I'm taking the supremum over all Lipschitz functions on X. So this is a metric, and in fact, this is a metric which metrizes the weak convergence of measures in Px. Well, with this notation, I am now in a position to formulate the first result. It's about exponential mixing. Well, in addition to the regularity, invariance and absorption, approximate controllability to point, and decomposability hypothesis, let's assume that the following conditions is also satisfied. For any u in this essential part of the phase space, and for any eta in the support of eta k, of the law of eta k, the range of the derivative of S, so S acts on the product space, so I'm considering derivative with respect to eta, so this will be a linear operator from E to H. The range of this derivative is dense in H. If this is basically approximate controllability condition for the linearized equation. So if this approximate controllability of the linearized equation is satisfied, then the Markov process associated with this random dynamical system has a unique stationary measure, and I can choose two positive numbers such that if I take any trajectory starting at any point, it can be also a random point in X, then the law of this trajectory will converge to mu in this dual Lipschitz metric with exponential rate. Well, of course, any other solution will also converge to this mu because X has this absorption property, but the rate of convergence will depend how fast your trajectory enters this set X. Anyway, this is not the point which is important for this talk, so let's consider solutions which start from X, and for solutions starting from X, you have exponential convergence to mu. Okay, so this is the first result, which shows that if you have good knowledge of your linearized equation, namely the linearized equation is approximately controllable, then you have exponential convergence. And now the second result. Again, you assume regularity, invariance and absorption, approximate controllability to a point, and decomposability. And in addition, you assume the following one. This is again about approximate controllability of the linearized equation, but in a weaker form. I assume that for any u, I have a set of L measure 1 in K, such that the range of the derivative is dense in H. So in the previous case, there was no almost every. It was for every eta in K. Now I assume that for almost every eta, you have this approximate controllability property. And in addition, I assume that S is holomorphic with respect to eta. Then again, you have uniqueness of stationary measure. However, I cannot claim that the rate of convergence is exponentially fast. I can just say that the rate of convergence is uniform for data in X, or it is even uniform for data outside X, but in any bounded ball. But I cannot say anything about exact behavior of gamma k as k goes to infinity. So why this theorem is relevant? Because when your noise is Fourier localized, then the linearized Navier-Stokes system is not controllable for all reference trajectories. So this derivative, there I can choose, I can present some etas for which you don't have this controllability property. However, under some additional condition, you will have almost sure controllability for almost all reference trajectories. Well, I will now very briefly mention. So I have basically 8-10 minutes left. I will mention very briefly how to apply this result in the case of Navier-Stokes equation. Sorry, I think I may leave this for discussion, if it is okay with you. Then I just go to two applications, two results about Navier-Stokes. So as I mentioned before, the problem of uniqueness of invariant measure reduces to the problem of controllability for the linearized equation. So let us consider linearized Navier-Stokes equation. So this is this equation, right? H disappears because I took the linearization, and you have just a bilinear term here, which now is linear because I fixed my reference trajectory u. Now here I wrote my right-hand side as a projection of zeta to some subspace H, because it will be convenient to write this way. And this H, as before, is one of the following two subspaces. The first one are vector fields which are localized in space. Sorry, it is not zeta over restriction zeta is equal to 0, or restriction to zeta of T2 minus D is equal to 0. On the complement, it is supported in D. Or the second time of noise when it is localized in the Fourier space. So I take finitely many EJ and I consider vector span of this EJ. So in the first case, you have a result which is due to Fursikov, Emanuilov, and in the more general setting to Guerrero, Fernandez, Cara, Emanuilov, and Puel, which says that if U is sufficiently regular, which is our case, then the dual problem of the linearized Navier-Stokes is observable. I didn't mention this concept, but this is a necessary sufficient condition for the controllability of the linearized equation, of the linear equation. So the dual problem, the problem is controllable if and only if the dual problem is observable. So that you do have this observability property, and therefore you have approximate controllability of the linearized equation, and therefore the uniqueness and exponential mixing. In the case of Fourier localized noise, as I mentioned, this is not necessarily the case. For instance, let us take the function, the solution, which is identically equal to 0. Then let's look at the linearized equation. Here's the linearized equation. When u is equal to 0, this term disappears. And you basically have a right-hand side which is supported by finitely many eigenvectors of the Stokes operator. Well, of course, such a solution, if you start from 0, and you do start from 0 because this is linearized equation, such solution will always stay in this subspace. Therefore, you cannot, so you have this property, Vt will be always in H lambda, and therefore you cannot expect, the approximate controllability is not true. However, you can impose the following condition on the right-hand side. So let us consider H lambda valued function and write it in this form. So I took my basis ej and multiplied by some functions eta j, and I consider this function on the interval 0, 1. I will say that this function is observable if you have the following property. For any Lipschitz continuous function ej and for any b, if you have this equality, then necessarily all of them is 0. All of them are 0. There are some noises for which this property is true, but I won't have time to mention them. And here is the result. It says that suppose that almost every realization of the noise is Lipschitz observable, and your set lambda is sufficiently large. Again, there is no time to mention what I mean by sufficiently large. Then, for any u0, for any initial condition u0, and almost every realization of the noise, the dual problem of the linearized system is observable, and therefore you have this weaker controllability property of the linearized equation, and therefore uniqueness and mixing for the stationary measure. And I would like to conclude with 3 open problems. Well, the first question concerns the rate of mixing for Fourier localized noise. Well, as I mentioned on the previous slide, for this problem, under some hypothesis on lambda and on eta j, you have uniqueness of invariant measure, uniqueness of stationary measure. So this eta j can be Brownian motion, and this is the result of Heirer and Mattingly, or this eta j can be just observable noise. This is not a result by Kuxin, Nersesian, and myself. So you have uniqueness of stationary measure. When h is equal to 0, you do have exponential convergence. The question is, what happens when h is non-zero? So the first open problem is to determine the rate of this convergence, which is true according to the theorem on the previous slide, and to prove to find some rate of convergence like exponential or something else. The second problem is the following one. According to the first result I mentioned for Navier-Stokes system, when the noise is localized, you have exponential rate of convergence, and this is due to the fact that you use diffusion rather than transport to propagate your noise in the phase space. The result about exponential mixing for Fourier localized noise, use the transport term to propagate your noise. Now, the natural question is it possible to use diffusion to propagate this noise to the phase space? And the second problem is that let's take one-dimensional noise, just eta multiplied by phi of x, assuming that phi is generic. For instance, if phi is the first eigenvector of the Stokes operator, then it's not generic. If it will always stay eigenvector when you apply delta. But suppose that this is generic in the sense that, for instance, it is a cyclic vector for the Stokes operator. If you apply L, if you apply your Stokes operator delta, well, it's not delta, but a Stokes operator, then you will get a dense, you will get a subset whose vector span is dense in the phase space. And indeed, if your transport term, if you put a small parameter here, epsilon, then you can prove the approximate controllability using by just one-dimensional control. The question is it possible to do something similar when you don't have any parameter A, you have just Navier-Stokes system? And finally, third open problem is the case when the noise is localized both in Fourier space and in physical space. Of course, this cannot happen, but you can consider this type of, what I mean is the following type of noise. You take your trigonometric basis, you multiply by them by eta j, and in addition, so there's a finite dimensional forcing supported by the first few Fourier modes, and you multiply it by a truncating function. So now your noise is finite dimensional and truncated. It's supported by a bounded domain, bounded subdomain of the torus. And the question is it possible to prove the uniqueness of stationary measure and the mixing property for it? Just to tell you that's not completely hopeless, I would like to mention the recent work by Nersessian, who proved this property for exactly this type of noise when you consider the complex Ginzburg-Landau equation. So in this setting, Navier-Stokes is a bit more complicated, not a bit more complicated because of the pressure term, but I don't think that this is a hopeless problem. So I think I will stop here, and thank you very much for your attention.
Thanks, Armen, for your talk. It was very interesting. And yeah, so I suggest that we move immediately to Leonardo's discussion. And then if there are any questions, we can, we have a small question session after Leonardo's discussion. So.
Shall I stop sharing?
Yes,
yeah. Okay, you did already.
Yeah.
I think you did already. It's not shared anymore. Yeah.
Yeah.
Is sharing now?
Yes.
You confirm?
Okay. So please go on.
So thank you very much. I'm going to continue Armen's talk just by talking about another equation and very similar problems. So my goal is to talk a bit about wave equations and discuss pretty similar things. So what do I mean by wave equation? I actually want to consider an equation which has a damping term, which is of the form some positive coefficient times the derivative in time of u. And then, of course, you have some random forcing on the right-hand side. And for sake of simplicity, we are considering the case h equals 0 when compared to Armen's talk. So the only forcing here is random and with 0 average. And cubic nonlinearity, because it's the easiest kind of nonlinearity you can consider and see something interesting. And of course, we're interested in the long-time behavior, so existence and uniqueness of invariant measures and mixing rate. And the very interesting thing is that in the case gamma equals 1, much of the project Armen was talking about for Navier-Stokes was already done, partly by Armen in the past. And I'm a bit surprised he was not mentioning this during his talk about Navier-Stokes. And the reason is that, well, not on the torus, but on a domain in R3, he already proved controllability with Amari, Duicars in 2016. And using their result of controllability on a domain in R3, Selmi and Nasfi managed to prove exponential mixing for the kind of noise Armen was talking about in the last slide. So this noise is both localized in space and localized in Fourier space. So first you localize in Fourier space and then in physical space, of course. And as I said, the proof of this is pretty straightforward, starting from the controllability result proved by Armen in 2016. What's something which is really interesting about the wave equation is that in some sense, the degenerate noise case is not very different from the non-degenerate case. And this is a feature of wave equation, and it follows from the fact that the equation is hyperbolic as opposed to parabolic. So, and why is that the case? Well, first of all, if the noise is high regularity, actually nothing changes. You can still use the controllability result by Armen, and prove uniqueness and exponential mixing of the invariant measure. The moment in which things start to go wrong is when the noise is very rough. So for the sake of this conversation, what I want to discuss is the noise which is a tiny bit smoother than space-time wide noise. And the reason why the theory starts to break down is that when you write down the equation and you write down the solution will have a regularity which is given by this sigma over here. So the solution will be in h sigma minus epsilon and not in h sigma. And this I should have written down. The standard theory requires u to be in h1. So as long as sigma is strictly smaller than 1, most of the arguments of the standard theory start to break down. And you need some more refined analysis. And since the typical solution will be in this space, then also the invariant measures will be onto this space. So you need to redo most of the theory. And the controllability result of Arman is not available in this case. And another interesting thing is that even if the noise is non-degenerate, it activates every Fourier mode, you're still missing the Stromfeller property. You're still missing the Stromfeller property. And this is still a bit surprising because formally this equation is hypoelliptic. If you look at the Lie brackets of the generators, you actually can span the whole of L2. So the fact that it's not Stromfeller might come as a surprise. And the reason again is given by the low regularity of the problem, together with some properties of the wave propagator. So if you look at the solution, you can see that the solution can be written as some stochastic term plus the linear solution of the wave equation plus a remainder. And the remainder will be a bit smoother than the linear solution. Actually, one derivative is smoother than the linear solution. And the problem here is that the linear propagator does not gain any regularity. So the solution will be in HS if and only if the initial data was in HS. So when you try to test Stromfeller, you can actually test it on functions which are of the form indicator function of the solution being in H sigma. So you actually, this is not a complete proof, but this is a good way to see that the Stromfeller property can't hold. If you try to compute the expectation of this function, so the difference of two solutions has high regularity. Because of this decomposition, you can see that the stochastic term plays no role in the difference. Here is the linear evolution, so you get the linear evolution of the difference. And this term is regular, so this term doesn't care. So this set doesn't care about the nonlinear term. So what happens is that this set is actually invariant. And of course, when you have invariant sets which are not empty or everything, it means that the Stromfeller property cannot hold. And the reason is that indicator functions are not continuous. So this is a weird property of wave equation that follows just from this property of the linear propagator, and that's why it doesn't happen for parabolic equations, because for parabolic equations you have infinite smoothing of the linear propagator. And from a practical point of view, what it means is that even if the noise is non-degenerate, you still have to use degenerate noise techniques if you want to prove some stability result or some mixing result. So, of course, there's not much time, so I can't really go into details, but something that I can say is that when sigma is positive, you need to do it a bit by hand. The standard theory doesn't work, but you can still prove the controllability properties that Arman was talking about. And what you obtain then is convergence in the Wasserstein norm, starting from any initial data in a certain Banach space. And something that is open is actually the rate of convergence, because in this paper, because of the low regularity, the energy estimates are much worse. And so what you obtain here is a subpolynomial in time, which is much worse than what you expect, which would be exponential mixing. Like, to be a bit more precise, this will be something that grows like the log of t to the -1. So it's really, really bad. And something a bit better should be true, even if you have no spectral gap, which I don't believe. I believe the spectral gap here, I would expect at the very least some polynomial rate of convergence. And what happens when sigma is equal to 0? The reason why it's interesting is that the invariant measure is known and is very famous, is the 542 measure times some white noise term on the time derivative. And here you have that the solution is actually not even in L2. So the typical solution of the equation when you're in the case sigma equals 0 is a distribution. And something can be salvaged, but as you can see, every time you go down with the regularity, you start losing pieces in the machinery. We started from something which had exponential mixing with very degenerate noise. We went down to uniqueness of the invariant measure and convergence, but without knowing the rate of convergence. And in the case sigma equals 0, this is a work in preparation. The best I can prove is that the 542 measure is ergodic. I can't even prove it's the unique invariant measure. And what I have is a very weak notion of uniqueness, which is that if you start from a smooth initial data, then you converge to it. But since the solutions are not smooth, are never smooth actually, what happens is that your domain contains very rough functions and the convergence result, and so it might be that there's very rough functions for which you can solve the equation, but that are converging to some other invariant measure. So in some sense, this is some kind of very weak notion of uniqueness. You have convergence starting from smooth initial data, but smooth initial data are not even in the support of the measure. And moreover, the convergence is the weakest possible form of convergence, is the one given by the Birkhoff's theorem. So it's only the time averages of the law that are converging weakly to the invariant measure. And I will say that then both uniqueness and convergence without the time averages are open in this case. Now, in the last 2 minutes, I just want to talk very quickly about the case in which the damping term is a function of space. And the reason I want to talk about this is that the problem has not been touched in the slightest, but it should be doable. And is because the long time estimates for the damped equation, even when gamma is compactly support, these are available. We know that without forcing, everything is converging to 0 at exponential rate, even if the damping is only concentrated on some very small region of the torus. And so in order to show uniqueness of an invariant measure for degenerate noise, or also for non-degenerate noise, all you need to do is to show controllability for the damped equation with this damping. And I believe this should be feasible, but I've never seen this, and I don't think it has been done yet. And this is all I wanted to talk about.
Well, thanks, Leonardo, again. And thanks again to Armen as well. So are there any questions from the audience?
Maybe I can ask a question to Leonardo. I mean, for the wave equation, it is a second order equation, right? So even if you have a full noise, full irregular noise, it's somehow, I can say that's the half of the dimension, right?
Yes.
So let's do the following thing. I mean, it does not make any sense, but let's try to do it. So let's write your wave equation as a system of 2 equations, right? So u dot equal v dot equal so on. And let's add artificially noise in the first equation.
Okay.
Will you have strong failure if it is irregular or not? Not even then.
If you do that, you have strong failure, yes.
Ah, yeah. Okay. Okay. So this is.
You know, it's still weird because the equation is apoelliptic. So you should expect. So of course,
Yeah.
you need one Lie bracket to generate the case. So it's, you know, it's not elliptic, but the apoelipticity is the best after elliptic.
Yeah. Okay. I see what you mean. Yeah. No, I mean, even for parabolic equations, even suppose that you have full noise, but which is just a little bit regular, you still won't have, even if it is formally, you don't need even a Lie bracket to generate everything. It is so formally non-degenerate noise, but you will never have strong failure, right? You agree with that? Yeah.
Yeah, there's a few.
Okay. I see.
You know, this is really interesting because it doesn't really depend on the noise. It just depends on the linear propagator. How the apoelipticity fails.
Yeah. So in a sense, so even if you remove the nonlinear term, you still don't have strong failure.
Exactly.
Yeah. Okay.
Okay. So yeah, I see Oleg has his hands up. So please, Oleg.
Yeah, maybe let me just ask a quick question to Armen. So when you mentioned these open problems, especially the first one, so were you talking about like very general noise, or what kind of noise you were talking about? Because at least in the Brownian noise, wasn't it solved by Hiron Mattingly in their papers of, 2006, 8, 11?
Well,
they show exponential convergence, or am I missing something?
They did when h is equal to 0, when there is no deterministic part of the forcing. I mean, at least I never seen anything written in that case. They do prove exponential convergence, but in their papers, h is always equal to 0.
Okay.
And
so similar, like in your second and third problem, so do you want the noise to be just the Brownian, or you want the result to be valid for like relatively general noises? So what is not known?
No, I think it is not known in both cases. So any result in that direction, I think it. Sorry, shall I share the screen or?
Yeah.
Or it's okay with you?
Just briefly remind.
Okay. Should be now. Yeah, so this is the first question, right? Determine rate of convergence, and for the second and third, I mean, you can consider both cases. It can be Brownian motion, or it can be just a bounded noise with some properties you need.
So somehow your point is that it's not even known, even in the case of the Brownian noise.
No, I don't think so.
Okay.
And I do believe that this is certainly not easy problems, but they are not hopeless, to my opinion. None of these three problems are hopeless, to my opinion.
Okay, thank you.
Okay, thank you, Oleg. We still have time for maybe one or two questions. Okay, so I mean, we are on time. So now we have a 5-minute breaks and we continue at 10 a.m. So thanks both again, Armen and Leonardo, for the nice talk and discussion. Yeah, so see you in 5 minutes.